Here in this particular problem, we have an underground pipe that has a water density of 1,000 kilograms per meters cube, and it says there's a fountain at the ground level. And it says here in the diagram, point A is 0.5 meters below ground level, and it says the pipe has a cross-section area of 1.0 times 10 to the negative 4 meters square. So the cross-section area here, where I'm circling with my cursor back and forth here, point A, that's given as 1.0 times 10 to the negative 4 meters square. And it says the cross-section of the pipe at point B is narrower, which is 0.5 times 10 to the negative 4 meters square. And it says the speed that the water exits at point B is given as 8.2 meters per second, and it wants us to find A, B, C, and D. All right, so if you need to, pause the video, read A, B, C, and D to yourself. Otherwise, I'm going to get cracking. All right, so let's go ahead and list out stuff that we know. So here, the cross-section area at point A, instead of 1 and 2, I would call it whatever it is here. This, instead of using 1 and 2, they call it A and B. So the cross-section area at point A is given as 1.0 times 10 to the negative 4 m squared right here in the wording. And then the water is going to flow through this horizontal pipe, and it's going to rise a certain amount of height, and then it's going to exit and shoot out. Okay. So the cross-section area is B, is also given as 0.05 times 10 to the negative 4 meters square. And then it says the exit speed at the ground level here is given as 8.2 meters per second. So there's the exit speed. I'm just going to call that VB for point B at 8.2. All right. So part A is not too bad. To find the speed at point A, all you have to do is use the continuity equation, only because you're given all these variables. So you're given A at A, you're given the area at B, and then you're given the exit speed at B. So really, hopefully this triggers the continuity equation. So therefore, I'm just going to set it up. Traditionally, it's A1V1 equals A2V2. However, we can just say at this location, we can just use the subscript A and B based on the problem given here. So I'll just do the cross-section area at point A times the speed at point A. That must equal to the cross-section area at point B times the speed at point B, because it's pushing the same amount of mass through the pipe in a certain amount of time. All right, so in order to find the speed at point A, all we have to do is divide both sides by the cross-section area of point A. So there we go. So I just move AA down to the bottom right. There's no adding or subtracting, so I can just simply do that by dividing both sides by the cross-section area of location A. All right. Really here, if you notice, we know everything. We know the cross-section area of B. We know the speed exit. We know the exit speed at point B. And then we know the cross-section area at point A as well. So I'm just going to go ahead and do a little plug and chug. So AB is given. VB is given as 8.2, and then the cross-section area at point A is 1.0 times 10 to the negative 4 meters squared, which is also given. So if you simplify all that, here I just cancel out units, but if you make sure all units are in SI units, things will cancel out naturally. And then last but not least here, I noticed in the top, for this particular problem, there's 10 to the negative 4, and there's 10 to the negative 4 on the bottom, so I'm just going to go ahead and cross those out. Therefore, really, we have 4.1 divided by 1, which really just gives us 4.1. So the entry speed in the underground portion here, the speed of VA is 4.1 meters per second, according to the continuity equation. All right, and that is the answer to A. Let's do B. B wants us to find the absolute water pressure at point A. So here's part B and C on this particular slide. To find the absolute pressure, to find the absolute water pressure at point A. So there's a certain amount of pressure here. Here in the wider area, V is given as VA, and then as it rises, the pressure up here is atmospheric pressure. Keep that in mind. So as the water exits into the air, the pressure at point B is just atmospheric pressure, which is just 1 atm, or you can convert 1 atm into Pascal. All right, so let's go ahead and do that. Let's go ahead and set up Bernoulli's function here. So the pressure at point A plus 1/2 rho VA squared plus rho GH at point A here, not point 1. So can you just mentally fix H1 to HA, and that also equals to all the stuff at point B. Okay, so here I'm just going to go ahead and define my reference point. My reference point would be the lowest point of this horizontal pipe at point A. So I'm just gonna call HA here is equal to 0. Once again, H1 is really HA. Okay, so I didn't fix the subscript there. All right, so I'm just gonna go ahead and cancel out rho GHA because height 1 or HA here is just referenced as 0. That's the lowest point in the water flow. From there, I can go ahead and solve for PA because ultimately part B here wants us to find the absolute water pressure in the pipe at point A. So we need to find PA. So mathematics speaking or algebraic speaking, to get PA by itself, I need to go ahead and move this 1/2 rho VA squared to the right side simply by doing the opposite operation. So it's positive here, so I'm just going to move it to the right side, which makes it negative. Everything on the right side is kept. Well, as I stated earlier, the atmospheric pressure at point B is given. So atmospheric pressure is 1 atm, and 1 atm is equivalent to 1.01325 Pascal. So this is a constant. Okay, so this is just 1 atm that's been converted to units of Pascal. And then 1/2 is carried down. Well, what's the density? The density in this particular problem is water, which is given to us as 1,000 kilograms per meters cube. And that's where the 1,000 kilograms per meters cube came from. Well, what is VB? VB is given as 8.2. Don't forget to square that. And then here's once again the density of water again, which is given as 1,000 kilograms per meters cube. G here is 9.8 because we're dealing with conservation energy here. So make sure you plug in a positive 9.8 and not a negative 9.8. Well, what's the height? Height at B? Well, I reference HA as 0, so therefore the water is going to rise a distance of 0.5 meters before it starts turning into a fountain here. So height here is 0.5. And when I move the 1/2 rho VA squared to the right side, it becomes a negative, so that's why there's a negative sign there. Plug in the density of the water, which is given. And we already calculated the speed at point A, which is 4.1. And don't forget to square that. Okay. All right, other than that, if you simplify all this work, the first time I kept the same because that's just 1 atm. That's been converted to Pascal. And then here, the second term, if you simplify that, that'll be about 33,620 Pascal. Likewise, the third term here is about 4,900 Pascal. And minus this last term, and this last term, if you punch in your calculator correctly, it'd be about 8,405 Pascal. All right, so simplifying that, that will give you an answer of, let's see, what is this? 131,440 Pascal. Or you can write it in scientific notation if you want. I just kept that as is. Doesn't really matter to me. Okay, so that is the answer to part B. That's how much pressure that exists at point A. All right, here is the part C. It asks us to find the maximum height above the ground that the water reaches. So here's the fountain. It's going to shoot up with a speed of 8.2 meters per second, and wants to find H max. So at this point, I'm just going to use kinematics. You can use conservation of energy if you want. Okay, so if you want, you can set up KE initially here at point B. That must equal to potential energy when it reaches this maximum height. That's entirely up to you. I'm just going to use kinematics here because this is now a kinematics problem. Here, I'm going to go ahead and cross out VF because at the peak of the projectile here, or the water as it shoots up, it's going to have eventually come to a stop and fall back down. So VF here is 0. VI I know is 8.2 because that's what's given to us. And when the water exits the pipe at point B, it was shooting off at a speed of 8.2 meters per second. Well, I know delta Y is delta Y is what I'm looking for, right? So therefore, I'm just going to go ahead and manipulate the function here to solve for delta Y. I need to get rid of the 2 and the G, so therefore it would just be negative VI squared divided by 2G. I carry this negative sign down, but now that it's a kinematics function, make sure you plug in negative 9.8 for G. So here VI is 8.2. The water at point B shoots off at a speed of 8.2. Don't forget to square that. And then G here is acceleration due to gravity. So as the water rises, it decelerates. And as it decelerates, obviously it comes to a stop, right? So acceleration in this case would have to be negative 9.8 because it's acting against the direction of motion, okay? All right, so negative sign here cancels out. So really, my delta Y, if you simplify it correctly, it would be 3.43 meters. But the question asks for height, which is a scalar quantity. So why I solve for displacement, I'm just going to leave my answer as a positive answer here because it asks for maximum height, and height is a scalar. So that is my answer, which is 3.43 meters. So the water will rise 3.43 meters before it falls back down in the vertical direction. All right, let's do part D. For part D, it says calculate the horizontal distance from the pipe that is reached by the water exiting at 60 degrees. So here, as you can see in the diagram, there's part of the trajectory is straight up. However, some of the water is kind of curving up here at different angles. So it dictates an angle here for us. So it's saying, what if the water exits at 60 degrees? So I'm just gonna go ahead and put VB here. I don't really care which is 60. So you have like three motion here to choose from, or three paths to choose from. I'm just gonna put that right there, not drawing a scale here. Okay. So V at point B here is given at 8.2, but it says 60 degrees. So I'm just gonna draw this. I'm just gonna draw that right there. That's about 60 degrees above the ground level. Well, this is now a projectile motion problem. So I think the easiest way to find part D is just to use the range function, because as the water exits the pipe here at ground level, it goes up and it kind of does this projectile motion problem and lands on the ground, which implies that it lands on the same level that it started from. So therefore, because my delta y is 0, I can use the range equation. So I made a note for you here. Only use the range function in projectile motion, if you recall, only if delta y is 0. So the water shoots out ground level. Watch my cursor. It goes up, curves down, and lands on the ground, which implies that it started off at the same y, ends at the same y, so therefore there's no vertical displacement. Okay, so I know VI is 8.2. I want to square that. A sine of 2 theta, theta in this case being 60 degrees, and then G here is 9.8. You don't need to plug in negative 9.8 because the range, whether you move left or right, will be the same distance. So in case you want, you could have drawn this blue arrow shooting leftward, but the range will be the same because it's the distance that's asked. Okay? All right. Again, what the problem says here, horizontal distance, just in case. Once again, you can totally change this blue arrow moving leftward, and the physics will come out the same. As you can see, this diagram is pretty symmetrical. So if you plug all this calculator in degree mode, so you would just punch in sine of 120, because 2 times 60 is 120, times that by 8.2 squared, and then divided by 9.8, you will eventually arrive at about 5.94 meters. So the horizontal range here, the total distance traveled horizontally, is about 5.94 meters. So I think this is the easiest strategy to use, assuming you are familiar with projectile motion functions and when to use these functions. Okay. Other than that, if you want, you can purely use kinematics. So here's the other alternative method for you. You can simply say that the displacement horizontally is equal to the speed in the x direction times the time of flight. Here, I put delta x is equal to VBX. Well, if I'm using delta x, I need to use the component, the horizontal component in the x direction. So here, instead of using just VB, I need to say VBX, right? Well, in this diagram, VBX is right here for you. Okay, here's my dashed line. So here's VB, which is the vector itself. So if you've done projectile motion up to this point, this component here is called VBX. So VBX would simply be VB cosine of theta, because the angle given to us is 60 degrees from ground level, which implies that it touches the x-axis. So therefore, it'd be cosine. Well, I can simply substitute that in. So instead of VBX, I can say VBX is VB cosine theta times the time. Well, I know VB is 8.2. I know theta is 60 degrees. The only thing I don't know is time. So what I'm going to do is I'm going to go ahead and find time using kinematics. I can set up the acceleration equation due to gravity, but here, and I need to solve for t, so I can just flip-flop g and t. So the time that it takes is simply the final velocity minus the initial divided by g. But what I'm going to do is I'm just going to go ahead and just find the time going up, because the time going up must be the same time coming down. So due to symmetry, I can find the total time simply by finding the time up and then multiplying by 2. Okay, so keep that in mind as you keep up with my work here. So for my strategy, I want to cross out VFY because I'm just going to find the time going up. So at the maximum height, VFY has to come to a stop before it falls back down or changes direction. So here, the negative sign gets carried down. VBIY is simply VB sine of theta, because according to this diagram, VB is 8.2, therefore VBX is pointing right, and VBY has to be pointing upward. Okay. So now that we know what VBI in the y direction is, we can say that it's just VB, the vector itself, times the sine of 60. G, we know what it is. It's negative 9.8. So I'm just going to plug that in. The negative sign gets carried down. VB I substituted for 8.2. Sine of 60 degrees divided by negative 9.8 meters per second squared. The negative signs will cancel out. Here is T. So this is the time that it just takes to go up. Okay. But keep in mind, we need the total time because the problem goes from this point to this point, right? It covers a certain amount of horizontal distance up and down. So I want to take this time and I'm actually going to multiply it by 2. So keep that in mind. I think this is just an easy strategy to do. So therefore, to find the horizontal distance traveled using kinematics, I would say VBX, which is 8.2. I carry that down, times cosine of 60, right? And then, well, how much time is it? It needs to be 1.45 seconds. So once you find the time that it takes to go up, you need to take this number and multiply it by 2 because you need time up and time down. But due to symmetry, the time up and time down must be the same, so we just take this value and times it by 2. So 0.725 times 2 gives you 1.45 seconds. And if you simplify this on your calculator, as you can see, you'll get the same value as you would use the range equation. Okay, so it'd be about 5.9 or 6 meters horizontally. Okay, all right, I hope that helps. Stay nerdy, don't be whack.